In this video, we're going to continue looking at our simplified view of how the internet layers work. And in particular, we're going to look at the middle layer, which is known as TCP/IP. Before we get too far into this, I want to remind us of one of the core concepts of using this layer model. And if you recall, we talked about a voice conversation message where the top two layers were the same as a postcard communication message. So what I want to emphasize is that the higher layers can communicate without any regard as to what's happening at the lower layers. And that's really important with our model and how we construct messages and send them back and forth. So when we're talking about our middle layer of TCP/IP, it doesn't matter if the lower layer is working over Wi-Fi or Ethernet or a cellular connection. It doesn't matter. Everything we're going to say now, moving forward, does not have to be concerned with how that physical layer is actually used. So let's take a look at how the middle layer, TCP/IP, actually works. Now I mentioned we're giving a simplified view. The TCP/IP layer is actually two separate layers. The TCP layer, which is a higher layer than the IP layer, but for all intents and purposes, we're going to consider them the same layer, just for simplification. Now, full disclosure, there is an alternative to TCP that is used in the real world, known as UDP, or User Datagram Protocol. We're not going to really discuss that, but I just want to make sure, for full disclosure, you're aware that some of the technologies that you use do not use TCP, although the vast majority of communication you use on the internet is actually TCP. So the first thing we're going to do is describe IP, or the Internet Protocol, and that's literally what the internet is named after, this IP, Internet Protocol. In order to send a postcard in the real world, you need a destination address. And usually you have a return address that you sent it from. Well, you need both of these to communicate on the internet. And to communicate on the internet, you need the same sort of idea. This protocol requires that you have a sending address where it's coming from, and you need a destination address of where it's going to. Now, this address does not look like our normal addresses we use for mailing addresses. They use a specific scheme to keep track of all the different devices on the internet. So what does an IP address look like? Well, it's 4 numbers. Each number is in the range from 0 to 255. So there's 256 possible numbers. And then you string them together, separated by period. Currently, www.uwaterloo.ca is really the number 129.97.208.23. If you launch your browser and you just type in 129.97.208.23, up comes the University of Waterloo. Now, that's not very convenient. We'll talk about a different way of addressing websites soon, but that is an example of how each computer or device on the internet has its own IP address. Now, unfortunately, we are running out of IP addresses. If you count up the total number of devices that can be on the internet, it's 256 times 256 times 256 times 256, which is approximately 4 billion different devices. When the internet was first being conceived of, that seemed like a perfectly valid number of IP addresses. But when we enter a world where each one of you may have multiple devices and there's lots of hardware that connects all of the internet, we have run and we are past 4 billion devices. So they had to come up with a plan B. There's 2 ways to address this problem. The first is what they call IP version 6. And the idea with an IP version 6 is that you'd have a much longer IP address. This is the actual IP address of another computer at the University of Waterloo that uses the IP version 6 scheme. With the IP version 6 scheme, we can handle 340 trillion devices on the internet. And that should serve humankind for a long time. The alternative scheme is called NAT. So you did not type in 192.97.208.23 into your web browser. You could just type in www.uwaterloo.ca. So what happens is there's a protocol named DNS, for Domain Name System. And what happens is when you type in www.uwaterloo, your computer sends that request out to your local DNS server, and it then returns back the actual IP address of what you're trying to connect to. So it converts between a more user-friendly human name to an actual IP address. Now, your local DNS server may not know exactly where uwaterloo.ca is, so it may go on to say, for example, the .ca DNS server and says, hey, you're in Canada, do you know where this address is? And then it may come back with the number. So it may require more than one hop to a different DNS server, but eventually, no matter what name you type in, it will come back. There is an international body out there that decides who can get what names. You cannot just go ahead and say, hey, can I be Microsoft.com? So what happens is you can register different names, and you can go out and register names for yourself. So you can have your own custom or vanity name, or if you have a business you want to start up, you can get your own name. And then what you do is you register that with an agency that associates your name with a real world physical address. And this is a controversial topic. There are a lot of each country. This is a controversial topic. There are countries that control their own rules for how you can get a name. So for example, if you want a .ca within Canada, and then there's other new top-level domains such as .ca, .edu, .org, and each of these have their own rules for how you can obtain your own name. At the end of the day, though, your computer just types in a name. At the end of the day, though, you don't have to really worry about this. You type in a name, and at the end of the day, though, you don't have to worry about this. You just simply type in a name, and your DNS server will resolve that to an IP address. Now, I mentioned that there's only 4 billion IP addresses out there. How do you get an IP address? Well, there's two categories of IP addresses. There's fixed IP addresses, and big companies like Google and Microsoft have their own fixed IP addresses, as well as organizations like the University of Waterloo. In fact, every number that starts with 129.97 is an actual University of Waterloo address. The University of Waterloo has that entire range. But you're just a regular citizen, and you want to connect to a network, whether you're at Waterloo or Starbucks or at your home network, and each one of your devices needs an IP address. Well, the way these on-the-fly or temporary IP addresses are doled out is known as DHCP, which stands for Dynamic Host Configuration Protocol. So the idea is your device, when it turns on and it tries to connect to a network, it sort of sends a message out, hey, I don't have an IP address. Can I have IP address, please? And then what happens is there's a DHCP server out there that has a bank of IP addresses that it can give out. And what it will do is will give you an IP address that you can use, and it also will expire after a certain amount of time. So if you go to Starbucks and Starbucks gives you an IP address, that's great. But an hour later, when you're gone, someone else can get that same IP address. And so the DHCP server just keeps track of addresses it has available and doles them out as needed. This is especially important for your mobile devices like your phone and laptops, where you may connect to multiple different networks. Now, the last tricky piece I want to explain, which will really help your understanding of how communication on the internet works, is known as network address translation. And when you connect to your home network or even Starbucks or places on the campus, this system is used so that we don't run out of IP addresses. So how NAT actually works is a little complicated, and I don't want to get bogged down in details. So what I'm going to do is give you an analogy using physical addresses that will just give you an understanding of how basically it works. So let's say we have an apartment building, and that apartment building has a physical address known as 555 Real Street. That's its real physical address in our world. But there's a whole bunch of people who live inside the apartment building, and they don't even know they're at 555 Real Street. They all think they live at Imaginary Lane. So one person might think they live at 100 Imaginary Lane, and someone else might live at 101 Imaginary Lane. So you may think you live at 101 Imaginary Lane, and then you want to send a postcard to your friend who lives at Destination Avenue. So you fill out your postcard, Dear Bob at 789 Destination Avenue, and your return address you put as 101 Imaginary Lane. And then what you do is you hand your postcard to the nice doorman who lives at Real Street, 555 Real Street. So you say, hey, doorman, can you please deliver this postcard for me? And he says, no problem. And then what he does is he changes your return address to be 555 Real Street, unbeknownst to you. And then he sends out the postcard to Destination Avenue. And then your friend at Destination Avenue gets your postcard, sees your address is 555 Real Street, and then sends it back to you. And then when it arrives, the doorman looks at your postcard and goes, aha, this is my friend who lives at 101 Imaginary Lane, and again changes the address from Real Street back to 101 Imaginary Lane, and then passes the postcard on to you. You were completely oblivious to this whole thing. The doorman was doing all of this managing for you. So what happens is we can have hundreds or even thousands of computers all sharing the same physical address. And this is another way of getting around this problem of running out of IP addresses. So when you go on your computer and you ask your computer, hey, what's my IP address? It might come up with a number such as Imaginary Lane. And in fact, if your IP address begins with 192.168, you live in Imaginary Lane. All right, we've just discussed a few technical issues that help us understand how the internet works and how the internet protocol works. But let's actually talk about internet routing, because that's one of the core parts of the IP protocol. Whenever your computer sends out a message, it has a destination IP address, and your computer sends that to a local router, and that router may send it to another router, and another router, and then another router, and eventually you'll reach the computer that it wants to reach. All of these individual routers are all connected together and are constantly sending millions of messages back and forth, and that's how your message gets from one side of the world to another side of the world. Now, how does this work? Well, let's discuss how it works in the real world. Say you live in Kitchener-Waterloo and you want to send your postcard to someone in England. Well, you fill out your postcard and you give someone's address in England, and then you take it to your local mailbox. And then someone picks up that postcard from the mailbox and takes it to a central depot. And they look at the address and they say, oh, this one's going to England, so I might send that to the Central Ontario Dispatch. I don't know how it actually works in the real world. I'm making this up. But we can imagine that it goes to a Central Ontario Dispatch, and someone looks at the address there and goes, oh, this is going to England, so they take it to a Canada Dispatch Center. And then at the Canada Dispatch Center, they look at this address and go, oh, this is going to England. Well, let's put it on this boat that travels to England. And then it goes over the sea, on some sort of big boat, and it gets over to England, and then someone opens it up and goes, okay, well, you want to go to London, England. So let's put it and let's give it off to someone who delivers in that region. And then eventually it'll get narrow and smaller, and eventually it'll show up at someone's house. So this idea of each person who looks at the postcard along the way knows, in general, which direction the postcard has to go. And it's complicated, but that's how all the network routers on the internet work. Whenever you send out a message, each one of them sends it to another router that'll get you closer and closer to your destination. Now, it's hard to visualize how all the routers in the world are connected. I stole this photo, and this is from 1999, so this is even a long time ago. But this is a visualization of many of the routers that exist in the real world. And so you can see how you might start in one corner of this giant network and make your way through a whole bunch of different paths to your destination at the other side of the world. In general, every message you send on the internet takes less than 50 hops, and a hop goes from one router to another router. That's still a lot, but you can reach almost any computer from any other computer in the world within about 50 hops. And that's how all of the messages on the internet get transmitted.